Hello, and welcome to the session on best practices to maximize BigQuery performance. My name is Jagan Athreya, and I'm a product manager for BigQuery at Google. I'm pleased to be joined in this session by Gary Steelman, who's a software engineer at Twitter. Hello, Gary.
Hey, Jagan. Nice to be here today.
Really glad to have you. We've put together a technical session for data analysts, data engineers, and data scientists. In short, if you like SQL, you've come to the right place. I'm going to start with a quick overview of the BigQuery architecture that drives the performance you see in BigQuery. Then we'll walk through a typical query execution within BigQuery. Next, we'll cover some of the best practices on how to write fast and efficient queries. And we'll also cover data processing techniques on the best ways to get data into BigQuery. Then I will turn it over to Gary, who will show you how Twitter uses BigQuery and will share some of his performance tips. Shall we dive in? Customers around the world rely on BigQuery performance to run their business. Spotify, which is a global leader in music streaming, analyzes hundreds of petabytes of data to give you the most personalized song recommendations. Their analytical queries went from 16 minutes to 33 seconds after moving to BigQuery. HSBC is a global financial institution serving 40 million customers worldwide. They were able to speed up their country liquidity calculations from hours to minutes and run their financial crime analysis 10 times faster with BigQuery. UPS, the largest package delivery company in the world, collects 1 billion data points into BigQuery every day and have used it to optimize their truck routes, saving $400 million and 10 million gallons of fuel each year. So let's explore how BigQuery can help drive performance for these businesses and businesses such as yours. So what makes BigQuery special? It starts with the true separation of storage and compute, which allows you to store petabytes of data in storage, but pay pennies per day for your queries. Data is stored in Colossus, which is BigQuery's columnar storage, which is encrypted, replicated, and distributed, making it highly durable against failures. When you send your queries to BigQuery, they run in stages over a massive farm of compute units called slots, which are units of computational capacity. BigQuery automatically calculates how many stages are needed for every query and dynamically calculates the slots needed for each stage. Data moves from the storage to the query server at lightning speed over the petabit scale network called Jupyter Network. Even complex queries, which need to store data between the query stages, have a persistent store called shuffle, which is entirely in memory. All of these put together is what makes BigQuery deliver blazing fast performance to you. Now we'll take a look at a sample query to see how it works within the BigQuery architecture. This is an example of a scan filter aggregate query on a table containing 1 billion page view logs from Wikipedia where the title contains Google. The queries are first routed to a query master, which contacts the metadata server to figure out exactly where the physical data resides and how it's partitioned to come up with the initial execution plan. The first stage of this query sends the query to a lot of parallel workers, each of which reads the title column and filter out the data that don't match. It then does a partial aggregation as directed by the group by and writes the results into shuffle using a hash of the title. The next stage reads from the shuffled output from the previous stage and does the final aggregation. The final stage, or stage 3, is extremely simple. It just reads the resulting titles and sorts them in an alphabetical descending order. This final sort operation is done on a single worker before serving up the results to the client. Now that we know how BigQuery runs queries, let's look at some of the best practices and how to run these queries fast and efficient within BigQuery. A typical query consists of a select, from, where, group by, and order by clauses. Since BigQuery is a columnar store, we're going to start off with how to optimize selects. Select star may actually drive up your costs if you have a really wide table with lots of columns. So the first tip I have for you is to use only the necessary columns in your select clause instead of select star. Next, when using functions, consider using approximate functions such as approx count distinct or approximate quantiles instead of the corresponding exact functions such as count distinct or quantiles. These approximate functions produce results which are 99% accurate if you're looking for trend data and not looking for exact values such as financial data. Now we'll come to where clauses where you can drive a lot of query optimization and efficiency. The key to improving efficiency is to filter early and use predicates which can be pushed down into the tables to filter out data, especially when joining multiple tables. Use the column directly to match values is a lot more efficient than applying a function on a column matched to a value, since this predicate can be pushed down. Next, we'll come to joins in the where clause. Any complex query involving joining one or more tables and finding matching relationships through the join columns. There are different types of joins, such as inner join, cross join, left and right join, which are well known. Speaking of how they're executed, joins are executed in BigQuery in several ways. A broadcast join is where a large table on the left is joined with a small table on the right of the join. In BigQuery, a broadcast join takes the small table and sends the entire table to every worker working on the large table column values if the table on the right is sufficiently small. To achieve this efficiency, you may need to filter and aggregate the data from the small table before joining with the large tables. The other type of join executed within BigQuery is a hash join, where you're joining large tables. Now, this is computationally more intensive. The goal of the hash join optimization is to ensure balanced data distribution across the joined tables. So keep an eye out for data skew. To give you an example of data skew, the number of cricket players per capita is skewed to the 12-member countries of the International Cricket Council versus the countries in the rest of the world. When this happens, you may need to query the skewed data separately from the other data and combine the results using union to maximize the efficiency of the query. A special case of join is self-join, when a data is joined within itself. This type of query can get very expensive. Some of the techniques you can use to get the data efficiently is to first take one pass at it. So for example, if you have a table containing male and female baby names, you can use an if function to create pseudo columns and compute both sets of aggregates in one pass. Another option, if you have multiple records with dependent data, for example, a start and end time and date for bike rides, you can use the lead and lag functions to specify a window within which you want to find the matching entry. To understand how these queries work, it is important to look at the actual execution plan. The execution plan for the query is available under the execution details for every query in the BigQuery user interface. It shows you the stages that the query took and provides the details of the operations and timings at each stage. Look for the waits, which indicates the stage that is waiting for a dependent stage to complete, which can often be a source of delay. Also look for variances between the average and maximum worker timings. This indicates that the distribution of work across the workers may not be uniform. Now that you've identified query inefficiencies, what can you do to improve them? BigQuery provides several data organization techniques such as partitioning and clustering to speed up your query and lower the cost. Partitioning in BigQuery allows you to divide large tables into smaller logical tables called partitions. Data for one partition is stored in a physically separate location from the other partitions, each with its own metadata. When a query is issued representing a specific partition value, BigQuery only scans those logical tables matching the partition value instead of the entire table. Partitions are usually designed for low cardinality fields, which is fields with a low number of distinct values, generally of the order of a few thousand. Clustering is a different form of storage optimization within BigQuery that stores the data in a semi-sorted format based on the cluster key, which may consist of one or more columns. You can use a combination of partitioning and clustering to optimize your query by identifying the low cardinality and high cardinality columns as candidates for partitioning and clustering. We recently announced support for partitioning of non-partitioned tables, so you can speed up key lookups for even high cardinality data which are not partitioned, such as user IDs. In addition to looking up queries, you can also improve the cost and efficiency of DML operations through partition pruning by using the underscore partition time pseudo column for ingested time partition tables, or by using the table or timestamp column for partition tables in your DML statement. The final recommendation for query speedup is the use of materialized views and BI engine. Materialized views are pre-computed views that cache results of a query for increased performance and efficiency. BigQuery leverages this pre-computed results from materialized views to deliver the results. If the data changes, BigQuery only reads the delta changes from the base table to compute the latest results, which is much more efficient. BigQuery is also smart enough to detect when a query can benefit from a materialized view and automatically redirects the query to the cache results of a materialized view instead of querying the base table from storage. BI Engine takes the speed improvements up another level by providing an in-memory store for BigQuery. To enable this, just reserve the BI Engine memory capacity in the same location as your dataset, and that's it. Your queries will now run fast and always fresh. To store and manage data, you need to bring data into BigQuery. BigQuery supports batch and streaming methods of data ingest. Data can be loaded into BigQuery from a variety of storage formats ranging from Avro to JSON. You can even use DML to perform ELT to transform data using the query API. We've removed the limits on the number of DMLs a table can process per day, which is much more beneficial to you now and is much more useful. If you need to perform continuous ingest, you'll need to use the streaming API to get more real-time information. If you need really accurate data that is still in the streaming buffer of partition tables, you can use an additional clause of underscore partition time is null to find the data that is in the buffer. Finally, we come to automation within BigQuery. While we have various ETL tools such as Cloud Composer and Data Fusion to perform various types of ETL, sometimes it may be more efficient to use BigQuery to run complex ETL operations. BigQuery supports scripting by which you can run a series of commands in a specified sequence with control logic such as while and if. And if you want to save these, you can save these as a reusable program called a stored procedure. It can also be used for migrating existing stored procedures from legacy databases when you bring them into BigQuery. This allows you to perform your in-data warehouse operations quickly without having the overhead of having to move the data outside. With this, let me now turn it over to Gary to tell us how BigQuery best practices are used at Twitter.
Thank you, Jagan. My name is Gary, and I'm a software engineer at Twitter. Today, I'm going to talk about how we use BigQuery at Twitter and some of the specific use cases we have, and some of the performance results that we've seen from using BigQuery's optimization features. So first, I want to go ahead and just dive right in and talk about how we use BigQuery at Twitter. It's important to understand the scale at which we use BigQuery at Twitter. We have hundreds of different users running queries and jobs every month. They're running tens of thousands of jobs every day, most of which are queries. We store data and run queries in hundreds of different GCP projects with thousands of different data sets storing hundreds of petabytes of data. As you might imagine, processing that amount of data uses a lot of compute power, and we're using over 1 million slot hours a day. It's important to note that at this scale at Twitter, that's why we care about performance so much. Every little bit of performance optimization we can make helps quite a lot. So now, let me talk about some of the different actual use cases we have for BigQuery at Twitter. We can think of these broadly in two different categories: analytics projects and adoption projects. The analytics projects you see here, I'll get into a little bit more detail later. But the adoption projects are ones that we can think of as already existing and migrating from a previous platform over to BigQuery. So for example, people are migrating from Google Sheets and Google Apps scripts, or on-premise Vertica and Solr clusters, or even using Google Analytics and moving their use cases to BigQuery. Teams who are adopting BigQuery are looking for big gains in performance and also maintainability. They're also looking for that rich integration with GCP tooling. So now, let me talk a little bit about those analytics projects in more detail, and some of the performance gains that we've seen for those analytics use cases. It's important to frame this discussion by understanding how we look at these optimizations at Twitter. We look at them at three different levels, kind of: the query level, the table level, and the project level. And a lot of those different features that you saw Jagan talk about earlier, you can see here categorized into the different categories. We make heavy use of all of these optimizations because at our scale at Twitter, every little bit counts. We also use the project level optimizations quite a bit, such as slot reservations and workload isolation. We try to separate workloads into separate projects so we don't end up with noisy neighbor problems. So now that we have an overview of how we think about these features at Twitter, let's talk about how we actually use them in some of these different types of projects. The first one I'll talk about today is this marketing project. The goal of this project is to generate an internal dashboard based on some filters, where the result of this report will actually be used to drive marketing insights and strategies internally. Generating this report requires running multiple BigQuery queries for each of the different sections of the report. So here, some of the first optimizations we made were to partition the input tables by time and to give the project more query slots to use. These two steps, partitioning the input tables by time and giving the project more query slots, are generally our very first two steps every time. The reason is because these are very low effort and very high impact steps. We will do this across most projects. Here, we also clustered the input tables by user IDs because that's what the report is keyed on. And we also scheduled a projection of necessary columns out of the source tables and into a destination table. In that destination table, we also join in a couple additional columns just so all of the data for this particular report is available in one table ready to go. Having all your data in one table like that is actually a huge speed up just in and of itself. As part of this, we also help this team clean up their queries by making small tweaks here and there, such as removing unnecessary order by clauses. All of these things together resulted in a 33% faster average query time and a 45% faster end-to-end report generation time for this use case. The next use case that I'll talk about today is the A/B experimentation project. This team already has an analytics use case running on-premise in Vertica. So in this case, we're migrating from an on-premise Vertica cluster into BigQuery. The goal of this use case is to fetch the results of A/B experiments on the Twitter product and render those in a UI. Users of the UI will actually use the insights they gain from the UI to drive product decisions. The interesting thing here is that the table that powers this UI has the high hundreds of terabytes of data in one place. We also have a very low latency requirement because this is powering an internal dashboard. So here, we partitioned these input tables by time again and gave it more query slots to execute. Again, we do this for almost every project. We also clustered these tables by more than one ID. Like Jagan mentioned, you can cluster by more than one field, and we want to do this in order of highest cardinality first to eliminate the most amount of data in a query as possible. We also selected only the necessary columns out of these source tables, whereas the Vertica query before was selecting all of the columns. And finally, one of the more interesting performance optimizations we made was using an array aggregation clause in BigQuery, where in Vertica we had been using a row number over clause. We use this to identify the most recent row in a set of rows to populate part of this UI. All of these things together ended up speeding up the queries by 55%. And the final project that I'll talk about today is a tweet analytics project. For this project, we want to generate a report of recent actions on entities. The interesting thing about this one is that we're migrating from an on-premise Solr cluster into BigQuery, and also the BigQuery table is populated via BigQuery streaming. The table is also massive. It's multiple petabytes of data in a single table. Here too, we partitioned the input tables by time, and we gave the project many, many more query slots to work with. We also scheduled a projection of the necessary columns to generate this report out of the source tables into a destination table again. Here too, we also saw a nice speed up with that. The most interesting thing that we saw here, though, is we had to tune our storage set sizes. BigQuery tables are backed by storage sets, which contain files which contain records. Storage sets have a maximum size limit. So when a storage set fills up with records, it actually gets committed and creates a metadata entry with it associated with the table. When a query wants to run on a table, it has to process all the metadata for the different storage sets to decide which storage sets actually need to be accessed. If there's a lot of storage sets, there's a lot of metadata entries, and processing a lot of metadata entries can actually slow down your query. So in our use case, we worked with Google engineering to increase the size of our storage sets. More storage sets, or larger size storage sets, means fewer storage sets overall because each one can hold more records. Because there are fewer storage sets, there is less metadata entries for a query to have to process, which actually ends up speeding up your query a good amount when you have a high volume of streaming inserts into a table. All of these optimizations together resulted in 33% faster queries for this use case. And that's the last use case I'm going to talk about today. I want to give a huge shout out to everyone at Twitter, cross-functionally, at Google PSO, and at Google Engineering for all the help that they have given up to today. Google has helped us build additional tools for Twitter internal data format. They've helped us build dashboards and administration tools. They've helped us increase DML efficiency by changing things in the back end. And they've increased limits in GCP all over the place for us. Some of the most notable ones are for VPCSC, or for the amount of data that a particular query can process in a single go. Without all of these things together, we wouldn't be near where we are today. And we're really looking forward to continuing our adoption and growth with BigQuery at Twitter. So thank you to everyone who's been involved. I'll pass it back over to Jagan now so he can wrap up the rest of this presentation.
I hope you found this session useful in some of the performance tips and techniques that we shared with you today. I want to thank my co-presenter, Gary, who shared his best practices of using BigQuery at Twitter. And I want to thank you for watching this session.